Yes. Next topic, discovery of other rays. Discovery of other rays and particles, you can write. You all know about X-rays. Who discovered X-rays and how were they discovered? Scientist W. Roentgen, Roentgen, W. Roentgen. TE, sometimes E is not written. If you remember, I told you about cathode ray experiment. Cathode, anode. Now, what W. Roentgen did, he kept some heavy metal like tungsten or molybdenum in the path of cathode rays. Cathode rays are produced, they travel from cathode towards anode. In the path of these cathode rays, he kept a plate of heavy metal like tungsten or molybdenum. He found when cathode rays strike this metal plate, some invisible particles are again produced, some invisible rays, not particles, some invisible rays are produced, and these rays pass through the glass of cathode ray tube. And if some photographic plate is placed outside the tube, if some photographic plate is kept outside cathode ray tube, these rays produced, they pass through the glass of tube, struck photographic plate and affected it. It means rays produced had high penetrating power. They could pass through hard glass tube of cathode ray. Now, he didn't know anything about these rays. Like in mathematics, we say that the unknown quantity x will calculate it later. Similarly, what he did not know anything about these rays produced. He named these rays as X-rays. And these X-rays were, their name was not changed. And till date, we call them X-rays. Now write down. W. Roentgen. T is generally not used. W. Roentgen found that when electrons strike, cathode rays are nothing but electrons. When electrons strike a hard metal like tungsten, symbol for tungsten is W, Wolfram, tungsten or molybdenum. Molybdenum is MO. Tungsten or molybdenum in cathode ray tube, some invisible rays are produced. These rays produce glow on zinc sulfide screen, ZNS screen, even if it is placed outside the cathode ray tube. Placed outside the cathode ray tube. Since he did not know the nature of these rays, he named them X-rays. Next paragraph. X-rays are not deflected in an electric field, not deflected in an electric field, which proves that they are not made up of charged particles. They are not made up of charged particles. They have high penetrating power, and therefore used to study interior of objects. Interior of objects. Now, in the next paragraph, we talk about the discovery of, about radioactivity. And the phenomenon of radioactivity was discovered by Henry Becquerel. What he found that from some substances, they spontaneously emit some rays on their own. Substances kept on their own without any light falling on it or any chemical reaction, they emit out some particles, some rays, and he named this phenomenon as radioactivity. And elements which emit out these particles, these rays, those elements were called radioactive elements. Basically, they emit three types of rays or particles. Mainly three types of particles or rays are: first is alpha rays, which are made up of alpha particles. I'll tell you about that. Second is beta rays. Beta rays are nothing but electrons. And third is gamma rays. Gamma rays are not made up of any particle. Like X-rays, they are high energy radiation, nothing else. Only this much small topic. Right on, next paragraph. Henry Becquerel found that nuclei of some isotopes of some elements, emit some rays on their own. He named the phenomenon radioactivity, and such elements are called radioactive elements. They emit three types of rays. Number one, alpha rays. They consist of high energy alpha particles which carry 2 units of positive charge, and 4 units of mass. Now, from this statement, analyze. 2 units of positive charge means there are 2 protons present in it. 4 units of mass means out of 4 units of mass, 2 units of mass is due to the presence of 2 protons. Remaining 2 units of mass is due to the presence of 2 neutrons. It means we can say an alpha particle is made up of 2 protons and 2 neutrons. Nucleus of helium atom also contains 2 protons and 2 neutrons. It means we can say alpha particle is nothing but the nucleus of helium atom. Continue writing. These are nothing but helium nuclei made up of 2 protons and 2 neutrons. They combine with 2 electrons to produce helium gas. Number 2, beta rays. They consist of negatively charged particles which are nothing but electrons. Number 3, gamma rays. They are not made up of particles. They are high energy radiations like X-rays. See, all these small topics will be required later in this chapter. Right, the next topic is atomic number and mass number. First item, atomic number. Within brackets, symbol is small letter Z. Atomic number Z is the number of protons present in an atom. It is also equal to number of electrons in a neutral atom. For example, sodium atom has 11 protons and 11 electrons, and its Z is equal to 11. Its atomic number is equal to 11. Next paragraph. Second definition is mass number. Symbol for mass number is capital letter A. It is the total number of protons plus neutrons, P plus N, present in an atom. Protons and neutrons present in an atom are collectively called nucleons. 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 Thus, A mass number is equal to Z, that is atomic number, plus number of neutrons, because Z is nothing but number of protons. Next topic. Now we'll be taking up many definitions. Next topic, isotopes, isobars, and composition of nucleus. Isotopes, isobars, and composition of nucleus. Apart from isotopes, isobars, we'll take up three more definitions. Right on. First, isotopes. These are atoms of the same element with the same atomic number but different mass number. Different mass number. So Z is same, but A is different. They contain same number of P protons, but different number of neutrons. For example, carbon 13, carbon 14, 6 protons, 7 neutrons, 8 neutrons. Number of protons is same, that is Z value is same, but number of neutrons is different. You know, chemical properties depend on number of electrons. And number of electrons is equal to number of protons in a neutral atom. Since isotopes have same number of protons, it means they have same number of electrons. And if number of electrons is same, it means their chemical properties will be similar. That on next paragraph. Since chemical properties of an element, depend on number of electrons, all isotopes of an element have similar chemical properties. Next paragraph, next definition. Isobars. These are atoms of different elements, with different atomic numbers, naturally, different atomic numbers, but same mass number. For example, if we consider potassium 40 and argon 40, they will have this has 19 protons, this has 18 protons, number of neutrons is 21, number of neutrons is 22. Mass number is same, that is 40, but atomic number is different because these are atoms of different elements. Next paragraph. You know, protons and neutrons are present in the nucleus of an atom. Write on next paragraph. Composition of nucleus. Composition of nucleus of an atom is represented as follows. Represented as follows. X is the symbol of the element. If it is potassium, in place of X will write K. If the element is chlorine, in place of X will write Cl. So this is symbol of the element. We write atomic number as subscript and mass number as superscript. Both Z and A can be written on the same side or can be written diagonally. That is your choice. Does not make any difference. So Z is atomic number and A is mass number. That's how we represent. Now, I'm sharing one numerical on this. Very, very simple. We'll solve it. This has been pasted 2 times. Please let me delete it once. Yes. And in today's video, this will find it. This you will find this numerical as in text numerical 2. See, you are given give notation of the atom containing 92 protons and 146 neutrons. Atomic number 92 is uranium. But if you do not know the symbol of the element, you can write the symbol X. So this is X. 92 is atomic number. Mass number will be number of protons plus number of neutrons. So if you add 92 and 146, that becomes the value of A. This will be 238. So this is the answer. X 92, 238. In place of X, if you want, you can write U. Uranium is the element with atomic number 92. Chalo. Next definition. As I said, there'll be 3 more definitions apart from isotopes and isobars. Next is isotones. I-S-O-T-O-N-E-S. Isotones. These are atoms of different elements which contain same number of neutrons. Which contain same number of neutrons. For example, chlorine 1737, argon 18, will take the gap of which contains same number of neutrons. Okay, we'll change this. We'll take sulfur 1636, 20. This is difference of 20. Have 20 neutrons each. So both contain same number of neutrons. They are called isotones. Right? Similarly, you can take the example of potassium and calcium. Potassium 40. There are different isotopes of potassium, 40, 39, and calcium is generally 40. So better we take this as 39 and calcium 40, 20, 19. Both contain 20 neutrons. So they are isotones. Next definition, isosters. I'll write I-S-O-S-T-E-R-S. Isosters. First of all, isosters are not atoms, they are molecules. Right? Right on. These are the molecules which have same number of atoms and same number of valence electrons and same number of valence electrons. For example, CO2 and N2O. You can see both contain 3 atoms, right? 3 atoms each. Now, number of valence electrons. This contains carbon, 4 electrons in the valence shell, oxygen, 6 in the valence shell. 6 twos are 12, 12 plus 4, 16 electrons. This one, nitrogen has 5 in the valence shell, 5 twos are 10, oxygen has 6, 16 electrons. So both contain same number of atoms, that is 3 each. Both contain same number of valence electrons, not total electrons, 16 valence electrons each. So they are isosters of each other. Last definition. Isodiaphers, D-I-A-P-H-E-R-S. Isodiaphers. These are atoms of different elements with same difference between number of neutrons and protons. Number of neutrons and protons. For example, boron 511 and carbon 613. In this case, neutrons are 11 minus 5, 6. 13 minus 6, 7. Number of neutrons in both. We have to take difference between number of neutrons and protons. And protons are 5 and 6. N minus P. This minus this 1. This minus this 1. So difference between number of neutrons and number of protons is same. They are called isodiaphers. Isotopes, isobars, these are widely used terms. But last 3 terms, isotones, isosters, and isodiaphers, they are rarely used. Next topic. See, in this chapter, you'll come across very important topics later. We are gradually building up the chapter. Next topic, atomic models. Atomic models. See, once we know about the discovery of electrons, protons, and neutrons, which are the main particles present in an atom, then the next question comes, how are these electrons, protons, and neutrons arranged in an atom? How did the modern structure of an atom came into picture? It started with Thomson's model, then Rutherford's model, then Bohr's model, and many other models. And today, what we know about the modern structure of an atom, that we study towards the end of this chapter. Right on, next topic, atomic models. Atomic models. So beginning part, you'll find easy because this is a repetition of what is studied in 9th standard or probably 10th standard. Right. To explain the arrangement of electrons, protons, and neutrons in an atom, different atomic models were proposed. Number one, Thomson's model of atom. Thomson's model of atom. Definitely from class 11 point of view, it's not important at all, but it's a part of the syllabus. We'll take up this Thomson's model in just 3 to 4 sentences, not much. I hope you remember this is also called plum pudding model, watermelon model. The entire atom is considered to be made up of positive mass, and negatively charged electrons are considered to embedded in that positive mass. What he did, he compared red portion of watermelon with the positive mass, or he compared pudding with the positive mass, and he compared seeds or compared uh, uh, whatever dry fruits, etc. we add to the pudding. He compared those things with electrons. That was the plum pudding model or watermelon model. So write down few words only. Uh, he proposed that an atom is spherical with positive uniformly distributed mass. Its approximate radius is 10 raised to power minus 10 meter. Electrons are uniformly embedded in it which gives suitable electrostatic arrangement. Stable electrostatic arrangement means attraction between positive and negative particles are uniform. Stable electrostatic arrangement. This is called plum pudding or watermelon model because pudding or red portion of watermelon was compared with positive mass and plums or seeds were compared with electrons. This model failed because it could not explain results of experiments conducted later.